at Ohio State on photonic crystal periodic structures, and went to Bell Laboratories in 1961 and did a lot of work on theoretical work on electron phonon and ultrasonic amplifiers, and went to IBM in the group under Leo Osaki in 1966, where he did, again, a lot of theoretical work on superlattices and the band structures and negative differential resistance. In 1976, he went to the Max Planck Institute in Germany under Manuel Cardona, and then he spent 11 years in a combination of energy conversion devices and Unicamp in Brazil. And in 1988, he went to the University of North Carolina in Charlotte. He's a fellow of the APS and received the APS New Materials Prize. And so he's going to address some of the issues with superlattices and resonant tunneling, and some of the work that started in IBM long before anybody imagined it would be useful for anything, the total mismatched band structure of indium arsenide and gallium antimonide. So, Ray, it's an honor to be able to introduce you and have you as our speaker.
Thank you so much. Okay, my thing is actually working, all right. What I'm going to tell you is probably a big surprise to you. Because I did something many years ago, as Jim introduced me. My thesis was in the photonic crystal. Okay, and what happened? The word photonic crystal disappeared. What happened? Okay, let me just very roughly tell you what happened. Department of Defense put a secret clearance on it. Pulled my master thesis from the library. Many years later, just about a couple years ago, I rediscovered. I went to the website, looked on the DoD sponsored by Sperry Gyroscope and Sperry Rand. I found it. It was declassified. The whole shipment, 45 pages, is on the web. Okay. Now this is another reason. There's another reason. When Isaki came to me, and he thought I was genius. How can I work in one weekend? I have theory all worked out. I never told him, because I made a judgment. If I would have told Isaki, being knowing who he is, he was, okay, he is, okay, most likely he would not pump his energy in to develop the superlattice. And I saw the idea about making a superlattice photonic crystal is really quite different. You know what the difference is? Let me just make a point to you. Some of you probably know what XF is in the band structure calculation. Band structure calculation, you track the movement of the electrons inside the solid. What XF is, you shine an X-ray onto it and trace the movement of, if you take only the first term, it's called Bragg reflection. We all use X-ray. But without realizing, XF was developed only because of the fast computer came. The most involved computer calculation is to calculate XF. It's called extended X-ray fine structure spectroscopy. What they do is that they shine an X-ray onto a piece of solid and track it, what happened after n bounces, okay? And it turns out the XF developed the whole shebang of the parameter we use, including temperature coefficient of band structure and including elastic constants of solids, all came out, all right? So all involved. So by that introduction, I'm going to go through my regular talk very quickly. Superlattices were introduced 45 years ago as man-made solids to enrich the class of materials for electronic and optoelectronic applications. Originally, Isaki and I recognized the need to make properties of small things big. That was all. As developed of nature, applying periodicity, the field developed to include quantum wells and quantum dots because of the role in phase coherence. Once the genie is out of the bottle, the field of superlattices is metamorphosed into surprisingly new twists. According to Bob Loom's Army Research Office, who published a memograph on superlattice, and there are 10,000 citations, okay, and there are 1,600 the publications plus all, well, you can actually read better than I can read here, okay. All right. There are plenty of similarity between superlattice and metamaterial. Today, metamaterial is big. Every time you open a journal, they're talking about metamaterial. But I'll tell you something about it. In fact, many aspects of these are presented for the first time. I've never told anyone about that secret that I kept from Leo Isaki, my boss. He was my boss, okay. All right. In 1990, while I spent a summer with Leroy Chen passed away, too bad. He was the one who operated MBE machines and all that. But you can operate all the MBE machines as you want. You have to have something else. And I gave him the something else. I used Raman spectroscopy to look at the phonon modes. Bell Lab used the optical property because the DH laser and all that, they have so much experience in the excitons. We did not have all the experience. So I told Isaki, I think the Raman would be very good. So anyway, that's what it is. We use Raman, okay? And after Isaki's Nobel lecture, 4 months before our manuscript submitted to the Applied Physics letter, Leroy Chen and I submitted, we said we succeeded making the man-made quantum tunneling through the we call it double barrier. It's because you have a quantum well with two gallium aluminum arsenide barrier on each side. And we apply the bias voltage. So when the input is at the conduction band, output is at the conduction band, the level is higher, so there's no current. You apply a voltage until you move up, line up, you get a big current. And that's called resonant tunneling. And it gives all kinds of interesting stories, okay? But I'm going to tell you all about. But Leroy Chen asked me, said, did you know our experimental result was in Isaki's Nobel lecture? I said, actually, I knew. Isaki never told me, all right, that he put out data into his Nobel lecture. But Isaki asked me to teach. We have a technician. He does all the programming or computation. His name is also Leo, okay, Leo Alexander. So Isaki asked me to teach Leo Alexander how to calculate the computation of the resonant tunnel, okay, as a function of voltage. All right, so then after that, he had a second thought. He came in, he said, hey, you know what, I think maybe you should write a few paragraphs for me too. So I wrote 3 paragraphs for him. It all went into his Nobel lecture. But there's one thing wrong. 4 months before we submitted to Applied Physics letter, and then Bell Lab, Ray Wolf, you probably know Ray Wolf. Raymond Wolf. Raymond Wolf was a famous man, also not as famous as you are. Raymond Wolf in 1959, he wrote a thesis. The highest thermoelectric material is called bismuth telluride. 1959, Oxford University. Did you know today, 59 is a long time away, 40 plus 14 is 64 years later. Did you know today the highest thermoelectric material is bismuth telluride? 64 years later, we have not made any progress. All right. Okay, now, wait. Okay, the next one. No, this is not the next one. Next one is this one. I'm sorry. I turned it off. Oh, I went backwards. The next one. Hey, what is that? I pushed the wrong button. Okay. Now let me just testing, see if it works. This one. Okay. This one. All right. I was working at Max Planck Institute. That's how I first met hair doctor Klaus Pro. And Isaki came and visited me at Max Planck Institute. So, all right, now, okay. All right, now this is the bombshell. Look at the date, 1947. L. Lewin, where was he? All right, L. Lewin actually was a member of the Royal Radar establishment. You know what it is? Electrical constants of a material loaded with small spherical particle on the crystal ladders. In fact, they did it on cubic ladders, and later on they did it on hexagonal ladders. And what they are doing, they are looking at the dispersion curve. The index of refraction. What's so different from the photonic crystal and the metamaterial? Metamaterial is a little different because metamaterial, they don't use God-made components. They use a man-made circuits. They put L, they put a C, they put a something. Now, okay, now let's see the next one. Next one is my thesis, okay? Kirschbaum 2, MTT7, 1959. Yovanovitch's paper was 1987, okay? 1959, you know what it is? Okay, oh, sorry. Okay, all right, now I got it, all right. You see this structure is called ridge waveguide. You cut the periodic structure on a ridge waveguide, all right? And Kirschbaum is an expert. Hey, wait a minute here. Okay. All right. Now I got it back. Okay. All right. Kirschbaum is an expert. Okay, the pointer is over here. I got it. He figured out you don't need to match the wave equation, use a block theory, and actually in one dimension it's called Fouquet theory. The mathematician figured it out a long time ago. And Felix Bloch said, hey, I'm going to generalize it to 3 dimensions. Big deal. One page, you generalize 1 dimension to 3 dimensions. You know what happened? They gave him a Nobel Prize. Okay, now, this is actually the measured, okay? One is Kirschbaum's method using circuits. The other is my method. Now, my method, I did not invent this method. I learned it from somebody working for Hughes Aircraft, okay? And I just found out from my friend. He went into the computer, found out Elliot actually passed away a few years ago. But his buddy is still living in England. They teach us how to calculate the dispersion curve, okay? So this curve, did I calculate it? Let me tell you what it is. I did not invent it. Elliot and this guy vied something. But later on, I'm going to show you the full reference to his paper. It's very ingenious. If you have a structure, periodic structure, all right, you use the wave propagating the direction of the periodic structure as a k-vector. Eventually, you want to find out what is that k-vector. But what happened to the side? The side perpendicular to that direction, you put boundary condition. It's a boundary value problem. The sides are taken care of. The direction along the wave is taken care of. So therefore, you have the propagation of a wave, okay? All right. Now, this is as you can see, the calculated and the crosses actually is the measured, okay? In other words, in 1959, we had it all figured out. Yovanovitch didn't. All right. Now, let me show you something else. No. Okay. Now, this is the one. This is the thing. The propagation vector here has m pi over w. W is the period. Okay. So this is in one dimension is called the Fouquet theory. But how do you have ax and ay direction? You have to match all the waves with all the common boundary. So in this complicated structure, I have to divide into 4 regions. One is this region. When the wait a minute, what's going on here? Okay, one is the order. No, I'm afraid to push the wrong button. So let me. Hey, wait a minute. I didn't even push it. I just touched it. It just went by itself. Okay, now, all right. I should have to touch it lightly. Okay. I touch too heavy. You see what happens? When I touch too heavy, it keeps on going. Introduction, very quickly. I joined Bell Lab. I published a paper for my master's thesis and so forth. I already told you all that story. I don't have to repeat it. I move on to the use of the Heisenberg's S matrix. Okay. You see, that's what happened. So there's another thing with it. DOD put a secret clearance on my work, and not only my work. Did you know there are lots of work, mostly in two places. One is huge. The other is Malibu's. It's also huge, actually. Yeah, they will do it. And they were actually doing it for the Defense Department. They were designing microwave lenses, all right? It turns out there's something else I want to tell you. One is the clearance problem, but there's a real problem. It's a technical problem. They made that thing. They put microwaves on the bench, it worked. They put their big antenna on there. It looked like a lightning rod all through because the metamaterial, photonic crystal, is a passive system. Passive system is ineffective unless near the resonance. Just like Fabry-Perot interferometer. You have Fabry-Perot interferometer. If you shine the wave away from the resonance, nothing happens. You have to shine the light near the resonance. What happened to the near resonance? Because the light keep on going back and forth, it builds up the fields. When it builds up the fields, what happened? Lightning happened. Breakdown. And then after that, Sperry Gyroscope invited me to give a talk, and they offered me a job to work there too. Then I have to remember something. No, I'm Chinese. I was, at that time, before I have a U.S. citizen, I'm Chinese. I don't want to horse around with a secret clearance and all that. Something might happen, okay? If something goes wrong, I'm the one to be blamed. So I stay away, all right? But another reason is that it doesn't work in the first place. You only work on as a toy. As a toy, it works. When you want to really make it work, they have a microwave antenna designed for one of our aircraft carrier. They try to shine the big power through those, ideally is a beautiful idea. A microwave system, you have a waveguide. The waveguide has complete control. Inside the waveguide, you have this rod. The rod, you just cut slots in it, all right? And you can control the index of refraction. You can actually make any index of refraction you want from the one we selected for 0.3. In fact, they can go from 0.1 to 10 index of refraction. So they can use that for a lens. But it didn't work. It only worked as a toy. When the real power puts through, breakdown. So I'm telling you this, that all of you do. Lots of the idea published in the Nature, one after another, all these papers published. It only will work as a toy. In the real system, if you want to put power through it, breakdown. Because you don't want to have a passive system operating in the very, very efficient place. What is efficient place? Within the resonance. If you operate within the resonance, the field buildup. The field buildup, it breaks down. All right. So now here I have given you a list of okay, there's a Lewin, 1947. Lewin wrote another book called Advanced Theory of Waveguides, or published in 1951. And Bluewine's work in 1953. That's the thing I really use in deriving that equation is from this Collins and the violin chord. And we discovered violin chord is still alive. He's living someplace in England near London. Okay, he's still alive, but Collins is dead. All right. And the Smith and that is, look at that. Fitzgerald letter, okay, this is something else. Kirschbaum too, okay. This is our paper, but I never show it to you, Saki. All right. And so we went ahead and making all that things without. Okay. Now there's some other thing I want on that slide. I want to tell you that. You see, I said, I move on to the use of Heisenberg S matrix after that was my master's. For my real thesis, PhD thesis, I wrote on the Heisenberg S matrix applied to electromagnetic wave. And when I went to Bell Lab, I naively submitted the whole thing to a journal. It came back. It said, obviously, this cannot be published because that's his thesis. He should actually reorganize, redefine, so in a way that people can understand what he did. I never did. So I showed it to my department head, Bell Lab. He said, put this away. You'll have time to do it. But right now, you better focus your attention. You know what my first job is? Don White and Andy Hudson invented the ultrasonic amplifier. And by the order of J.R. Pierce, because it was exactly the same as Pierce, what do they call it? Pierce traveling wave tube. Traveling wave tube. It's the same there. The only difference is that you use gallium arsenide. Did you know gallium arsenide has very high piezoelectric constant? If you launch the electromagnetic wave through gallium arsenide, you put a phonon detector on there, you'll find out a lot of sound wave can come out. So all you do is make a p-n junction of gallium arsenide. All right. Use the p-n junction to launch a sound wave. Then we put a high voltage on the gallium arsenide until the electrons are going faster than the speed of sound. Speed of sound is only 10 to the 5th. Speed of light is 10 to the 10th. 5 orders of magnitude higher. So speed of sound, we can actually put the voltage on, and particularly we lower down the temperature to liquid nitrogen temperature and all that. Guess what? Bell Telephone Laboratory put 96 PhD on their project by the order of J.R. Pierce. Because Pierce envisioned, now finally, the traveling wave tube is only traveling wave tube work for microwave. It does not work at higher frequency. Now, this phonon traveling wave tube, it may be working at higher frequency, but it didn't work. You know why? Breakdown and noise, high noise. Thermal noise very high. So therefore, you see, when you really come to a device, the device really have to work. It takes a lot more. The ultimate thing is that I call them, the things do not work, I call them toys. You can always sell the toys, but you cannot sell the device. Okay? All right. Now let me move on. Oh wait, I'm pushing the wrong button again. You know, I'm getting old. Old people never learn. You know. When Leo showed me his disclosure, okay, Leo wrote a disclosure. His boss was Bob Keys. I don't know anyone knew who Bob Keys is. Bob Keys was early people working on the phonons from General Electric before he went to IBM. IBM research firm, they are very jealous of Bell Lab. So they raided two places, Westinghouse and General Electric. Took their best people from Westinghouse, General Electric to IBM. Right after that, you know what General Electric did? They changed their name. General Electric Research Lab changed the name to General Electric Development Lab. their research guy all went to IBM. Okay, but anyway, so Bob Keys, Isaki's, actually, I asked Isaki, I said, would you show me his original? He said, no. Bob Keys just basically threw it away. So I went to Bob Keys. Bob Keys likes hiking, so I go hiking with Bob Keys in the wild. So I'm friendly with Isaki's boss. So I asked Bob Keys, I said, could you show me what you did to Isaki's disclosure? He said, all right, I'll show you. One slide. You put Isaki diode in series, okay, many Isaki diode in series. Wonderful IV characteristic will develop. Period. Bob Keys put a red mark across and said, disclosure closed for lack of operating procedure. That was it. So then I went to Isaki, I said, hey, Bob Keys, show me your disclosure. He said, yeah, I told you. He closed it. I said, he has the right to close it. Because you should at least say that you're putting them periodic. He said, oh, yes, they are periodic. Why would I put two different diodes in the same thing in series. He said, periodic. I said, okay. But then I said to Isaki, I said, periodic I'm interested because I did not tell him that I did the work on the on the serrated ridge wave guy. I said, I think I know how to calculate the negative resistance. He said, negative resistance? Did you measure negative resistance? I said, yes, just like your tunnel dial, you have negative resistance. Are you interested? I think if I had negative resistance. Now I tell you where I learned about the negative resistance. When I left Bell Lab, I was actually tried to be a theorist. I wrote a paper on the phonon Green's function, okay, and all these very complicated things. So I get to know Cornelius Herring. Why? Because Cornelius Herring called me up, said, it's about time you and I met. He said, because your department head refused to sign off your paper. Because in those days, if you write a paper, you want to send it to the publisher at Bell Lab. Yeah, of course, their invention disclosures involved and all that. But it has to go through 8 department heads to approve. So my boss said, I don't know what you wrote. I wrote a paper called Cherenkov radiation of sound by a charged particle moving through a solid. So he gave it to Cornelius Herring. Cornelius Herring read it through. He said, that's good work. Okay, all right. So he approved it. After he approved it, he said, all right, I sign off your paper. But he said, maybe you and I should get together more often, because by looking at your work, he said, you know who I am? I said, yes, I know who you are. You're the head of the theoretical physics department. He said, well, maybe we should get to know each other. Okay. So I go to Cornelius Herring's office maybe once a month. All right. I get to know him quite well. So that's my background. I'm very strong in theory. Okay. And then when Isaki came out, there was a book written by Brian Pippard. Brian Pippard, on his first chapter, he said, do you know why Bloch oscillation has never been seen in metals? He said, because the electron, the scattering time is 10 to the minus 14th of a second. You need 4 to 6 orders of magnitude better scattering time in order to see the Bloch oscillation. You know what Bloch oscillation is? It's Bragg's reflection in X-ray. You put the X-ray into it, it's going back and forth. It's a Fabry-Perot interferometer. You put a line in there, it's going back and forth. If you have periodic structure, it's going back and forth. It's called Bloch. And then, if the electron die away before it ever come back, you never have. Okay, you want the electron to have mean free path about 3 period before you can see the effect. All right, and I read his paper. Then I thumbed through a few of the pages down. There's a method to calculate the transport property called Chambers method. Okay, and Pippard pointed out, the Chambers method is very simple, because you know what we do in ordinary physics if it's too complicated? We take sines and cosines for oscillating terms. We take e to the plus or minus alpha t for going up, we call gain. Going down, we call loss. All right. So therefore, if you would take that kind of a statistical system, the Chambers method of called the method of phase is very simple. So it's 2 lines. That's in my first paper, Isaki and Su's paper. We derive what the NDC, why it came from the superlative surface. Why? If electron going back and forth oscillates, okay? All right? No scattering, all right? Plus and a minus cancel each other, you get 0 current. So if you have scattering, you get current. The more scattering you have, the less is the current. Okay, all right. So now, but on the other hand, if you have no scattering at all, you get 0. So therefore, if you apply a voltage onto any system, it go up. If the electron still oscillating, it will start come down. That's a negative resistance. Negative resistance is the basis. If any of you taking a course in the first year electrical circuits and all that, maybe not first graduate course in electrical circuits, you will learn if anything has a negative resistance, it's an amplifier. And that's what we do. We want to amplify. When we amplify with a feedback, we can oscillate. All right? So everything fits in. Okay, now let me just move on very quickly. Okay, now, so in other words, okay, people, I already mentioned it. All right. Now, Leroy Chen left IBM, went to work in the Millie Dresser house for a year and a half as a sabbatical. And he was coming back, and too bad, when he came back, he was stuck with a piece of equipment. Isaki asked me, said, do you know somebody at Bell Lab used to work there? He said, I know Walter Brown. So I called her Walter Brown. He said, you and Isaki are officially my guests. Come and visit me. So we drove down from Yorktown Heights to Bell Lab to Murray Hill. And we told Walter Brown convinced us. What you need is called dual plasmatron. Any of you in this audience ever heard of dual plasmatron? You have. It's a piece of junk. It's a piece of junk. And we didn't know until Leroy's advisor was Gerard Pearson. So he gave Pearson a call. Okay, Pearson said, do a plasmatron. Did you open it yet? He said, no, not yet. He said, don't open it. Just ship it back. It's a piece of junk. So then Pearson told Leroy, you should use MBE. All right. So Leroy mentioned to Isaki the MBE, and Isaki right away went to England looking for the MBE builder. Vacuum generator was the when you came over, we have MBE machine from vacuum generator. And we made a system. It didn't work. Okay. All right. Then when he you were joking with it. You said, I don't think your work is your samples are very good because Isaki smoked cigar. And I believe it because he was joking with me, I took it seriously. Isaki smoked cigar. So I told Isaki, maybe you should stop smoking cigar. He said, why? So I told him what you said. He said, it's impossible. He just keep on smoking cigar. I said, you keep on smoking cigar. Don't blame us. We cannot make good devices. Until one day, Capasso invited me to give a talk. You were sitting next to me. And you told me, you said, do you know why your work at IBM is not very good? You put 50% aluminum, 50% gallium. You should not exceed 0.28% aluminum in the gallium aluminum arsenide alloy system. So we dropped it back. All of a sudden, we got the exciton peak and all that all looked very good, very much like, because at Bell Lab, because Henry and Dingo was the guy. Dingo was the main person. Whatever happened to Dingo? He formed a company, right, to making retinal tunnel devices. But anyway, okay. So what I want to mention to you is that, okay, you keep looking at the watches. So I know that I'm trying to stop. Okay, but before I stop, I want to mention something to you. Most of the things that turned out very good for us, it was not something that we planned by accident. So therefore, life is full of accidents. Okay. Well, let me just very quickly. Okay. Leo, I'm sorry that I voted no. Oh. The reason why we went into the retinal tunnel diode, because Isaki, we finally succeeded having a negative resistance. Okay. And Isaki asked me. He was giving a talk with 100 people at IBM. He passed out to vote for confidence. Then he asked me, did you count a yes and no? I said yes. About 80% said yes. He said, now I have the mandate to go on with the super legacy. All right. Ian said, not so fast. You guys rediscovered the gun effect, but this time internally alloys. So everybody believed gun. Marshall Nathan at that time was executive boss. Marshall said, we should stop that, or that nonsense, because gun effect, he can make better gun diode than you guys are doing, okay? So then I went to gun effect. I told you, what happens if I have only one aluminum gallium arsenide on both sides with a gallium arsenide quantum right in the center? Now, if you arrange the voltage at which you move the input, line up with that state, it goes right through, random tunneling. If you move away more, it drops back. It has negative resistance. It has everything. He said, if you do that, I'll be the first one going around the wood on your behalf. So we told Isaki. Isaki said, Gun is very clever. He knew we cannot do it. Pinhole is going to kill us. He did not allow us to do it. He only allowed us to do it after he knew the Nobel Prize was for him. Then he jumped in. So what happened? The random tunneling was something not planned. Okay? And type 2, type 3 superlattice today is very big. You know why? If you have a valence band higher than the conduction band, minimum, okay, electron will go from the valence band to the conduction band. All this work we did with the plane wave doesn't work anymore because the valence band, conduction band, the U part of the wave function are orthogonal. So you have to mix them. How do you mix them? Interaction. It's just like band structure calculation. If you have state 1 and the state 2 mix, you form linear combination of the two. All right. So I made one simple, it took me only about a couple of weeks. I generated idea. I went to Isaki's office. You know what? You told me to find a way to find the voltage at which the negative resistance starts to turn down closer to the zone center. So we would be applying a low voltage for NDC. But it turns out something good, because now if you put them farther apart, they don't interact very much. It's a very narrow gap developed. If you put them closer and closer and closer, the interaction per unit distance is large. You open up big gap. So you have band gap and the width on design. That is a type 3 superlattice. Today, many of the detectors, like Rezeki, those people that brag about all their, they're all type 3 superlattice. Okay. But where the idea comes from? By luck. I didn't invent it. Nobody invented it. Because we are trying to do something else, and you end up with something else. So the life is like that. So I think I want to just stop here by Nobel lecture and all that. Ao Cho told me, I told you that story. Original type 2 superlattice, I told you that story. Okay, now I did mention to audience. Okay, here I want to show you something. To be more live with you here, yeah. I did mention to audience in the conference in 1995, Snowbird, Utah, organized by Craig Taylor, that I have seen this work before, published in England. But Eli replied that, I did not believe me. Okay, he did not believe me. Okay, at this point, Jim Mertz, you probably know who Jim Mertz is. Jim Mertz was the guy, the #1 expert in exotons at Bell Lab. Jim Mertz stood up and said, he also became a big shot in Santa Barbara. Jim Mertz was the one organized Santa Barbara, started with all that big activity at Santa Barbara. Okay. Later on, he became director of research. Notre Dame. Jim Mertz stood up and said, when Ray said he has seen this work, I think this work existed. Period. No more discussion. Okay. But now, should I feel sorry that this work was actually published before? Eli did not invent this at all. Somebody else did. the thing is that he honestly didn't know. But because he didn't know, he just assumed I was trying to pick. I wasn't trying to do anything. I was trying just to point out that it has been done before. All right, now let's skip all that to the last one, because I know that you want to move on. Okay, Capasso. Oh, okay. I want to take 1 minute by telling you how I feel about Capasso. I told Capasso, I said, I tipped my head. Leo and I, we did not understand what a device is all about. We talk about bulk. In reality, there's no such thing as a bulk device. There's input, there's output, there's something in the between. It's called interaction. All device. And what Picasso did, not Picasso, Capasso, what Capasso did, he designed a system with input and output and interaction with quantum wells. All right? So he can adjust them to the design he wants. Because he understands what the real device is. There's the input, there's the output, there's a things called interaction. Isaki and I, we did not understand that point. You know, how can you say a big man got a Nobel Prize, a professor like Ray Zhu, that we did not understand? We did not understand that. We really did not understand. Okay, now I'm really wrapping it up with my last one. Okay, thank you and all the best to you now. But before that, one thing is clear. Okay, look at this sentence. One thing is clear, that it is possible to hide one's work from public awareness, because most people do not read someone else's work carefully. Thank you.
So thank you very much, Ray, for a very illuminating talk on some of the early history and controversies in our community. So I think what we should do is we ought to just move ahead. We'll just maybe clear our plates and things at the break. So maybe let's see, Kurt and Gary, and who was the third? Just two of you. All right. All right. Young-Heng has a few words of.
Okay, I just say a few words. I usually say.
All right.
Yeah, I think it's a. I hope everybody enjoyed the presentation so far, and I try to summarize what I have learned and I couldn't learn by reading their papers. For instance, now I just learned that French coffee is so good. I can keep you asleep until 5. I won't sleep until 5 a.m. And also I learned that don't believe other people say in their paper from uptown. And also I think I also learned that from Fujitsu, it's Professor Hiyamitsu's talk, and never ever give up, even until to the very last day you get fired. So you should not really give up at all. And also I learned from Professor Horikoshi is that sometimes you do want to work with your enemy, use your competing technology to test your idea first before you invent anything new. And now this last one I think I like probably the most, and just I think students may like this as well. So do not worry if you don't publish any paper in 3 years. Okay, you will be still employed if your boss is is as nice as the Max Planck Institute. So that's my summary of the talk, and also I hope you enjoy that. So now before I give the microphone, the next session chair, I just want to say a few words how we organize this particular session. I think this particular session we invited people actually who build MBE machines, like Paul when he was very young, and also we invited people who who run MBE labs. I think, for instance, there are two people. One is Albert Fischer from Max Planck, used to be at Max Planck, and the second one is John English from UCSB. So I was lucky enough to be in both groups. I saw these two, I call this probably two largest MBE group in any research institutions, how they are managed and how people can, or students can learn from them. And also we invited people from industry and professional research institutions like Sandia National and Hughes Research Lab. So they will share with you how research is done in industry. And now the particular, the special guest I propose and we have invited is Professor Anupan Madhukar. I personally like his story about how a theorist become MBE goer. You know, he comes from a very strong theoretical group, and he will tell you how that happens. The last, not the least, that as we heard this morning, the MBE will not fly until it is very useful. So I think the Professor Shibasaki from Japan will tell you how MBE is used to manufacture whole devices, which are used every day, everywhere, even in cell phone, many places. So, yeah, so this is my brief introduction. I will hand it over to the session chair.
Thank you. I'd like to first thank James Gupta for putting this together. He did all the legwork, but unfortunately he can't be here. So Kurt and I are just going to do the easy jobs of introducing the speakers. So we're shifting a little bit in gears. We're now into a more rapid fire session. There's a bunch of talks here by MBE experts about things that went wrong and other entertaining stories. It's listed in your program, the speakers are listed alphabetically, but we're actually going to bring them up here chronologically. So the earliest work that we're talking about here is going to be Paul Luscher's talk. Paul's going to talk about some early vacuum work and related things that vary in all the way back to the 1950s. Oh, okay.
Great. Which advances the slides now? Okay, got it. Well, good afternoon. Hope you had a great lunch. The title looks really long, but I have tried to keep it within the 10 minutes. I'll do my best. And the point is, what I'm trying to do is get a retrospective snapshot of how research and commercial development enabled and supported MBE's birth, which we've seen so much of, and its explosive growth, which is exhibited here and outward. And I'm going to start back in 1950 because this is very much related to vacuum. The objective of this presentation is to present specific periods in time in a manner that will allow us, I hope, to experience, at least for this moment, the unique experience that the pioneers, I guess that's us older people working back in there, experience looking forward. Not looking back and saying, that was obvious, or I've got one of those, but looking forward. If you can put yourself in that position and along this fascinating journey. So vacuum, for 30 years, 10 to the minus 8 torr was assumed to result from a failure of the pumps. And the reason was the pressure's lower than 10 to the minus 8 torr. It had undoubtedly been achieved, but because of the well-known X-ray limit, at least it was now well-known. It wasn't very well-known to the vacuum people, even though the people making electron tubes for your radios and so forth, they knew about it, prevented it from getting there. And it wasn't until 1950 that Baird and Alpert introduced the BA gauge, and basically this allowed them now to measure pressures that went down to 10 to the minus 10 and lower. So this is as if you went to the store between 1950 and 1960 to get your stuff. So I apologize for the gimmicks, but I got 10 minutes. Here's the, laser, right? So the BA gauge came on, and that demonstrated that, in fact, they were able to get lower pressures. And the C-stellarator that was occurring at Princeton, the RCA electron tube division was developing the hardware, and it was basically a DIY, do-it-yourself, for UHV systems. And this is where a lot of this began. The shear seals, the copper shear seals, the valves, all of this was contracted out and made. And it wasn't contracted out to a company that necessarily just specialized in that. And so bit by bit, they began to make process. These were mercury diffusion pumps, often in tandem. They were what I found in my lab at the University of Illinois. In fact, Al and I missed by about 3 or 4 years, I think. I arrived somewhat after you left, so no wonder we're in this field together. These are the gold wire seals that Al was talking about. But fortunately, in 1957, due to the need for klystrons and keeping them clean and the penning gauge, Lou Hall, Bob Jepson, and John Helmer developed what was the vac ion sputter pump. And this worked really well if you didn't have large gas volumes to handle. And so by 1960, they developed a commercial version which they could begin to offer to put on ultra-high vacuum systems and also a dry pumping system. So now we're already up to 1960, and you're able to get the vacuum pump and so forth. Wheeler came out with the conflat flange. The nice part about that was you could bake that over 400. It almost never, ever failed. It was sexless, and you could begin to buy hardware for that. And this is the Wheeler flange, so these are the conflat flanges. They began to actually build and sell commercial systems. As you saw, Al could submit a set of plans, and they would build a chamber for him. And there was a lead project that was started by John Helmer in conjunction with Lester Germer as a consultant. And so the work that Bell had shown in the post-acceleration display work was actually made available by Varian early in '62. So that was beginning to see the beginning of some of the surface analytical equipment that you didn't have to build yourself. And apparently Al bought a gun from them that he didn't have to build himself, but it was a little overpowered, I guess. They dropped it, I think, down to 10. He'd came out, that's what Norm said. He said he didn't sell too many. I think, Al, it wasn't until you started showing what it would really do in an MBE system. I mean, they were spending time with this. What are they going to do with this, okay? We'll get there. That's the system I had. I'm really glad I didn't have time to show you the older systems that we had built at Illinois. I mean, we had people like Alpert and Probst and Gerd Ehrlich and Edgar Luscher, and they were influenced by Homer Hagstrom. CSL at University of Illinois was a bastion of this. So and the CMA had just been introduced right as we went through this period. Now, non-UHV epitaxial growth yielded very high quality epitaxial materials. Everybody's been talking about that. Except they had a problem. They had really, as we know, severe difficulty in achieving precision, high precision and an atomic resolution in the device structures. So all we really needed were these things that everybody's been talking about: clean, stable evaporation sources, fast shutters, a heated substrate, a slow growth rate, low substrate temperature. We got the UHV system. We're all set to go, except we had to have group 5 elements incorporate with group 3 elements to better than 1 part in 10 to the 8th. You're evaporating 3 elements. You've got to hit stoichiometry. Wow. Non-equilibrium chemistry. The growth front had to be atomically smooth. It looks so simple. Impurities incorporated had to be less than 1 in 10 to the 8th. UHV isn't all that clean unless it's hydrogen, and you hope it's not going to stick in the temperature you're growing at. Sticking coefficient is low. So why are these pioneers smiling? I mean, wow, I love these 2 pictures. I think they're really, really great. And I appreciate them allowing us to use it, and I'll talk a little bit about it. Now, John Arthur, that was his early work. He's talked about it, where he looked at the reflection of the gallium and arsenic beams. I didn't have the other slide. He sent me one. That's the gallium reflection, and he showed, looking at the arsenic and the gallium, that stoichiometry could be achieved. And then this is Al's system, which he showed you, which he built it and set up, and that's that super duper heat gun. I didn't realize that was a 50 kV gun. I just looked at the thing. Anyway, with that, he was able to produce this. And what did that show? That showed that during the epitaxial growth process, the surface became smoother and smoother until it became atomically smooth. So we had layer by layer growth leading to atomically smooth surfaces, with the exception of some debate here, but very, very close. This enabled the growth of superlattice structures that looked very much like this. And this was really pretty impressive. And then I went to a conference after I joined Varian. I joined Varian in '75. And that's where I saw Ray Dingles, Wigman, and Henry show that they could actually give me an example of Schrödinger's solution of a particle box. We had to do this, you know, and I was finally glad that we could make one and have one. And this was the exciton that's shown in the absorption spectrum. You can see the degeneracy lifted as they narrowed the aluminum gallium arsenide wells. And then Dingle, Gossard, and Wigman went further, and they narrowed the aluminum gallium arsenide, and they showed that tunneling could take place. And at this point, I was completely, between Al's work and this work, completely convinced that this was absolutely fantastic. But I needed something to do. So here we are in 1975 now, and vacuum systems and surface analysis instrumentation had become commercially available between 1960 and 1970, as I showed. The Varian Vacuum Division was fabricating custom vacuum systems for MBE scientists. Al has shown those examples before this time. And MBE components, however, the components that went in there, as we've talked about, were strictly do-it-yourself. So the question was, commercial availability of these components, should they be able to accelerate the development and the acceptance of MBE and all of its remarkable capabilities? So Varian decided to offer a commercial MBE system. So in 1975, Tom Cooper in marketing and myself in engineering with a designer, a master technician, began a project to deliver a vacuum chamber and all the components necessary to grow high-quality 3-5 atomic level structures. Now, at the same time, Varian also had a microwave division, which is solid state, and an R&D effort in its corporate labs, which it was setting up to do molecular beam epitaxy as well as LPE and VPE. And as Al has pointed out, those people always gave us a hard time, right? So we did that. We needed 8 custom furnaces on our design crucibles, cooled baffles and liquid nitrogen cryopumps, high-speed furnace shutters, and 2-position heated substrates. So in 1976, less than a year, Varian actually displayed the MBE 360 at a booth in Chicago at the AVS Symposium, and then later in October in Zurich, Switzerland, and announced their setting up of the Central Research Laboratory facility, which was going to be quite a big help. And so this is what we put in to that vacuum chamber. This is the liquid-cooled baffles, which isolated the furnaces. These were the furnaces. These were the shutters, which were buried. The liquid nitrogen cryopump, which sat right behind a baffle, which would keep the shutters from being exposed when they were open. The shutters were all based on a sinusoidal actuation so that they didn't vibrate, and the bellows would have a really long life because it was rocking. And here's the reed gun, which was already well known, the standard components, and a 2-position heated substrate holder. Okay, that's what it looked like. It was real. That's the main shutter. It's open. When that closes, it protects the CMA. Some people actually liked having the ability to rotate right around. Other people wanted another chamber. But at least one additional item was required to make rapid progress in the device growth and to demonstrate a production capability. And that was, what else? The load lock. So the MBE 360 was designed so that lead system, which I didn't think anybody was ever going to use because they had reed, would accept the load lock when the chamber was rotated. I just hadn't gotten to it because management was focused on silicon. I needed some help encouraging management to provide the resources. I've heard some other needs to encourage management here. Provide the resources to implement my load lock design in a timely fashion. And who better to help than Herb Kromer? And I got this off the way, and I love this picture. I went down to visit her because there you have the theorist with the wrench, which is all the hardware, with this focused gaze, which shows both the intensity and the drive to get this done. So I sat down with Herb, and I showed him my design for this load lock because, as Al said, I wanted this to be able to be removed after the sample was transferred in. But if you wanted just a single metal valve, these were made for accelerators, and they were so expensive, they were $5,000, that if I could put 2 Viton seed valves in series, you bake them open, you close them. If there's a little bitty leak, the differential in there is like 10 to the 13th. So it's just not going to get in. The bonnets did need to be changed to metal, and if you still want to buy metal, they're making better metal valves now. This pump would also evacuate the load lock. Now they went to cryo pumps and so forth. So Herb reviewed the design and decided he wouldn't accept anything less. And I'm very grateful to Herb for going back to Varian and telling him that he would not accept anything less because this made it possible for Varian to deliver it to him in a timely manner and all the rest of Varian's customers going forward. So in 1978, that was the system. And yes, Doug Collins, who's here today, he was in the corporate labs. So you can see we did have the MBE 360 in there, and then we did upgrade it by rotating it and putting in the load lock. Okay, but liquid encapsulation, Czochralski and vertical gradient freeze were producing ever larger and higher quality wafers. And this meant that cross-wafer uniformity had to be vastly improved if we were going to grow with the production market requirements. Okay, so Al Cho and K.Y. Cheng demonstrated that rotating the wafer, they told me, he said, rotate the wafer, you'll be fine. And well, I looked at some of the designs where they had heated walls, and as the distribution began to change as the level changed. So we went and set up a glass slide, and we took a graphite crucible and filled it with silver, and we evaporated on that, and you got a curve that's something like this. I had to reproduce it. I can't find the old data. But this break right here is exactly where the walls would come, and that's without rotation. As soon as I rotated it, actually Walt Nodal was doing the work, it was pretty flat. So it was a little flatter than that, actually. So we figured if we tapered the crucible, we could get out further, and that's the results that we got, and we were able to get better than 1% over 2 inches. And the reason we were using silver, by the way, is aluminum and graphite didn't work well. I didn't have time to talk about the disasters, but the furnaces really looked pretty bad after one run. They were gone. So we developed what we called the continuous azimuthal rotation unit, which was known as the CAR, and the idea was to have a reliable unit that would continue to rotate during deposition. It has a beam flux gauge in the back that you could turn to calibrate. So the MBE Gen 2, in response to this increasing wafer size and uniformity requirements, a joint task force was undertaken by Varian Associates and Bell Labs, which in this case turned out to be represented by Jim Wong and Jim DiLorenzo, to design and manufacture an advanced MBE system to greatly improve uniformity, which at that point was over 2 inches. It was, I think, up to 4 inches now in the modular versions. Throughput, because it got bigger, purity, and flexibility. And so in 1981, you could go out and purchase a system to get the work growing. And this not only had the continuous azimuthal rotation, it had a separate preparation analysis chamber which allowed us to outgas samples. This transfer rod never got exposed to atmosphere ever. The 6-wafer loader would allow us to load into that. We had the Auger out here. And this particular unit also had dual Temescal E-guns with 3 additional ports in case somebody wanted to do another metal or silicon. And it was more than they needed. You don't see that today, but it was in fact in the system. And this is what the one that was shipped to Bell Labs looked like, and 3 of them were shipped at that point in time. I think one went to Fujitsu, one went to Bell Labs, and one went to Hewlett Packard. So Varian was also in device production at that time. 2 of those were installed. That's Tom Hurl. He went out to form QED, which was eventually bought by IQE. And this just shows that, in fact, the same deposition we got in uniformity also showed up in the breakdown voltages and saturated drain current of the hyperreactors, and this shows the capacitance being linear as we expected. That was done with Tom Hurl. So Varian was using this as well. So today, if you go to the store, this is what you get. Anything you want, you can just go and select it. Now, there's some people in here I don't think you can get because I didn't filter out everything that Google put up there. But if you want surface analysis equipment to put in, you can go to the store and you've got it. So there's a big difference now from what it was. And I don't know whether I was able to give you a forward-looking view by taking these periods when vacuum was so difficult to do to now where you still have to find what is a disruptive technology to really change things. And that is what was done in MBE, and I hope that the work that was done commercially made it easier and easier to do that. But it doesn't take away the need to do the disruption. I'd like to thank all of the researchers and institutions that went well before me, that helped set it all up, to the researchers who taught and encouraged me, to all my colleagues who shared a passion not only for this marriage of technology, but the value it created, to all those customers who I found to be great collaborators and teachers and made my days fascinating. I enjoyed this field more than just about any other because I was working with scientists and researchers that every day was a new challenge. The Varian and its amazing pioneers, and they really did, from the Klystron days and the vacuum days, have a lot of good people that came out of the accelerator business who invested in this vision, helping accelerate its development and acceptance. And I want to thank all of you for the opportunity to meet here with you today and share my time in this business. I hope you saw it from the perspective that I saw it on each step from the time I hit graduate school with all the great people who built that institution, who helped me through that, brought me there, the people I worked with all around the world, and made my life so interesting. Thank you for the time. I'm not sure I quite got it, but I do appreciate it.
Thanks very much, Paul. So I think chronologically, our next jump is up into the early 70s. We're going to hear from Eldrush Fisher talk about the beginnings of MBE at the Max Planck Institute in a warehouse.
Hello, everybody. My name is Albrecht Fischer. I was working more than 20 years in Max Planck Institute in Stuttgart, and right now I'm the CEO of Createch. You'll find our booth outside, but I will not talk about this. I will talk about the beginning of MBE and MBE laboratory in Stuttgart, 1974. I was a co-worker of Professor Ploog since August 1974, and we started in the provisional laboratory in the MBE in the Max Planck Institute. Here, this one, which was used before we moved in '75 to the new institute in Stuttgart. This provisional part here from the institute was too small for our MBE, so we have been in an extra professional room, and this was in a warehouse near to this institute, maybe 300-400 meters away. And this was a small room divided from a big room, and the big room was covered with a lot of whiskey bottles. But we could not use them because there was a big wall and we needed to make MBE. And so we installed this MBE system in autumn '74. Klaus Bock told you that we have decided to use an MBE UHV system from Ribera, and this came in '74. And we grow the first MBE layer in March '75. So you see, this was the system itself. This was a little bit from this time right different to the systems right now. You see here the O'Shea, the QMS, the sputter gun, and all the things which we had inside. And you have here a view inside where you can see we had here, oh, I'm sorry, this was the wrong one. Let me see. So, this one. So, this one. You see here, the most important thing are the fusion cells, otherwise we cannot go any layer, you know very well by yourself. And we have a vertical system here with 3 or 4 fusion cells here inside. We have here a manipulator with a small sample. We have here an investigation tool. This is a special quadrupole, which was developed also in this time from Ribeir. Much more complicated as right now these quadrupoles which we have in use and which you switch off and everything is working. And we have a sputter gun here, so we could make sims. And we have an electron gun here for doing read. And on the other side we had a O'Shea, also from Ribeir this time, where we could investigate maybe how to remove oxygen from samples, from surfaces and so on. What we do not have was a load lock chamber, because this was not available at this time. So you see, when we made a sample exchange, we had to open the system. We had to remove the sample, to mount in the new one, to close it, to bake it, and so on. So we could make at least, let's say, 1 or 2 layers we could grow by week, and not by hour or by day. So you see a little bit this fusion cell pot. This was a cylindrical liquid nitrogen shard, and the fusion cells have been here inside. You see here this a little bit from outside. The problem was at this time no PBN was available, and the materials from which we could produce the fusion cells was made aluminium or this kind of maybe hot pressed bonitrid or hot pressed aluminium, and this is not very good for standard or for a good fusion cell. So, but no other materials was available this time, so we had to do these fusion cells, which we had to produce by ourselves with these materials. And I can show you in this slide that, for example, this the insulator was looking a little bit funny from today's view. This was a part from aluminum oxide, covered then with tantalum wire for heating, and this an out part for insulating. And inside was a crucible made from these materials which I told you. And we had, you see here a little bit. See here, this was the crucible, the outside here, and all the crucibles have been, or the fusion cells have been together, so there was an influence of these crucibles and so on. So this was not so optimized, just like today's setup for MBE systems. Another problem was that we condensed always material here on this fusion cells, so we could not. We could really not do long-term growing or growth, because in a short time the fusion cell was closed. And the other big problem was we had a type K thermocouple and not a type C, because type C ultra-high vacuum feed-through, just like now, was not available on the market. So we started with type K thermocouples, and we recognized that there was a degradation in arsenic atmosphere over 1 or 2 months, so that means this was not very useful to use this kind of thermocouples. And the other thing was, you see this influence, and so to avoid this with this tape K thermocouple, we made a special homemade system. We had a good glass blower in our Max Planck Institute, Mr. Sprader, and he was able to produce a ultra-high vacuum feed-through made from quartz glass with this tungsten wire inside, and so we used this kind of ultra-high vacuum type C feed through instead of this, which you know, which you know right now, which is well known in the market. The next problem was at this time the sample holder itself. This was a manipulator. You see here, this is very small sample holder with a very small sample on it, 10 by 10 millimeter. But this was not the problem. The problem was the load lock that we had not in use, so we could not. We have to open the system all the time. So there was no. The loading here was you had to unscrew here the sample holder to demount it and to mount in the next one. And we had here also a Faraday cup and so on. So this was the manipulator. We learned also at this time that maybe, for example, these wires made from copper and so on, that all was degraded due to this arsenic. So we made a lot of, from today's view, a lot of funny points which we learned. But at this time it was a little bit more stressy, I would say. Okay, so the next point was we could not use an arsenic rod just like now, because you could only buy on the market arsenic lumps, and to fill this in a crucible and to fill it with the maximum intensity that you have most possible arsenic inside. We cracked these chunks into small parts and in a glove box, and then we filled it in the glove box in the effusion cell. That means we put in the complete effusion cell into the glove box, filled it in, moved it out with some protection covering, and opened this covering at the machine and put it in the machine. So nobody can imagine right now what this means with the arsenic, for example. And the next one was, you see right now, the most laboratories have fully automatically liquid nitrogen supply rods and so on, so vacuum isolated. We had this not. We had to use this kind of small tank here, and this was the complete liquid nitrogen supply for the machine. And because we was not in the institute, in this professorial institute, we had to bring this tank from the institute, where a big tank was for filling. We had to bring this tank by a car to our laboratory, and because the car was very small and was no secure to put or to transfer this kind of tanks, we sit together with the tank in the car, and the car was moving from the institute to our laboratory, and we were hopefully looking that we see no police and nothing else, and this was a little bit funny. And another point was, Joe talked about this 50 kV gun. We also got a 50 kV gun from Ribera, and it was developed by Monsieur Bizot. You told the name. This is chief engineer, was at this time from Ribera, and as you some of you can imagine that the prototype is not running from the first time. It was necessary that Monsieur Bizot came sometimes to Stuttgart and developed a little bit more in this reed thing. And when he could not, we could not repair it or improve it in our lab, then he take it with him to France. And at this time in Europe, we had a lot of borders. So every country had a border to the other country. So we needed custom and all these things. And to avoid this, Monsieur Bizot always took the nitrane, the nitrane, what was the name? Maybe the nitrane to Paris. This was his Oriental Express, now I know it. And in the nitrane he smuggled this big 50 kV gun, maybe up behind his luggage, and the next time he came again with the night train. And once we worked very long in the evening, and when we wanted to go out from this warehouse, the warehouse was closed, and we had no key for the main entrance, and therefore we needed to use a way over the roof with this big gun on the shoulder, and we had to climb down, and this was not so easy also for Monsieur Bisson. And but you see, it was then working very long for a very long year, and maybe it was very successful, this kind of development. And at last, you see, we have not grown only MBE layers, we have also grown grapes. And how you unload MBE layers from a load lock chamber, we unloaded our grapes from the vineyard, and this is a very more hard job as when you use maybe a load lock chamber. Therefore, we had, of course, to fill up our energy, and there we are here, and you see here Klaus Blog was also very busy with unloading grapes. So, thank you very much.
Thanks, Elbrecht. Next up is another MBE researcher that dates back into the early 1970s, Anupam Madhukar from University of Southern California.
Okay. Well, my hand shakes quite a bit, so I generally do not like these pointers. Goes all over the place. Anyhow, as has already been mentioned, first of all, let me, of course, thank the organizers and Dr. Zhang particularly, and so on, to give me this opportunity, include me in this illustrious group that I've admired all my life, at least professional life. But, as has been said, I was a theorist, and I have been a professor almost 4 decades. So let me start by simply pointing out, I chose this title, and of course, Shakespeare understood that a rose, its essence is what matters, not its name. And that has generally been my theme in everything I have done in scientific life. Words, I believe, are ultimately our biggest enemy when you start thinking about the frontiers of conceptual science. It is the choice of words that limits our ability to express ourselves. It causes controversy, it causes a lot of misunderstanding, etc., etc. So I want to avoid controversies that may come from words, but at least get to the concepts. Second, since I, by education and training in the first 10, 12 years of my professional life, was a theoretical physicist, first particle physics, then condensed matter, etc. So my way of thinking generally comes from that, or I'm very lazy as an experimentalist. All the work is done by my students. And so that also affects my thinking of what to try and do without worrying about how difficult or hard it would be. That I always find out later. In any case, so I also had a remarkable combination as a graduate student at Caltech, that from the physics department, I had the unique privilege of having Professor Feynman on my committee as the chair of the committee, and at the same time, since I became interested in some solid state kind of things, which in the 60s didn't exist at Caltech in the physics department, I went over to Professor Paul Douay in material science, who is the person who invented splat cooling and what has followed from that, metallic glasses and things of that nature. So the issue, and this goes to the point that was being made earlier, Dr. Cho made that point, that when you come from an exposure to different fields and backgrounds, often the way you cross-fertilize things and concepts flow one from the other, and your ability and desire to look for what is in common becomes a very different kind of experience. So that is what has happened to me. Professor Dewey's great influence is my almost obsession with metastability. That, I believe, is at the heart of everything we do in our community. And so with that in mind, let me get on with the real thing that I want to talk about. This I didn't bother to read to you, but I figured that because I am a professor, I've been a student all my life, and because there are a lot of young people here, I thought letting them read this while I'm saying the introductory remarks was a good thing to do. So let me move. My interest in MBE got started in 1973 fall when I was at IBM Yorktown Heights in an accidental conversation in the IBM cafeteria with Leroy Chang and Liu Saki. And I was actually by background at the time a theoretical guy, but working in two categories of problems. One was chemical reactions on surfaces, chemisorption, metallic surfaces, chemisorption, and Dean Eastman at IBM at that time was one of the pioneers, along with Bill Spicer at Stanford, from some of the earliest work on chemisorption metallic surfaces, which included things like carbon monoxide, carbon dioxide, etc., nickel tungsten, etc. So the issues of surface chemical reactions and adsorption and so on were my work. Some of the earliest theoretical work in the early 70s is from me in that area. Second, in March of 1973 at the APS March meeting in San Diego, Professor Alan Heger, who used to be at University of Pennsylvania at that time, had announced possibly high temperature superconductivity in organic linear chain conductors, 1:1 salt, TCTF, TCNQ, that family. So a lot of effort everywhere in the 70s, starting following March meeting, was focused on linear chain conductors and transport in one dimension and so on. And the Smith and Style paper of 1972 PRL, which had the silicon inversion layer, two-dimensional electron gas, all of that was my background. So with that, we come to this conversation, and I learn, and what they were telling me was, is in fact in their paper, that paper by Leroy Chang and co on. And you can see, it says, the deposition process at the substrate, on the other hand, is far from thermal equilibrium situation and is governed mainly by kinetics. That appealed to me, given my background, and I asked one simple question in that conversation, which is paraphrased, I don't remember exactly, but it went something like that. How does the molecular arsenic dissociative reaction kinetics affect the formation of the interface? Because it was trivially self-evident that at room temperature, if you do that, you got nothing. So by definition, you need some enough thermal energy to make arsenic break up. And so my view from that first conversation was that the essence of this subject is understanding surface molecular reaction, incorporation, and metastability, and that this is all far from equilibrium. And with that, the conversation ended, and I moved on. I went to University of Chicago. I was there for years. I go to USC in '76. And by this time, a few developments were occurring that I have noted down here. You guys can read that faster than I can read it to you. But basically, by '76, when I arrived at USC, I had a senior colleague by the name of Professor Murray Gershenson, who was a chemist. And you will see that this field is dominated by chemists, actually, at least from my perspective, starting with John Arthur's work. So Murray Gershenson got interested in MBE, and I had a graduate school friend who was a chemistry guy, Frank Granthena, who was in this MBE business. He retired from JPL a couple of years back. And Frank and I were graduate students, I in physics, he in chemistry. So when I came to USC in '76, I hooked up with Frank, and everything I know about ultra-high vacuum, X-ray photoemission, etc., and later on MBE, I know it from Frank. Unfortunately, Frank is not here, but he is my teacher in everything. So the way it all converges is very simple. Frank gets an MBE around 1978-79. This is the Ribeir's 1001 model. And my colleague, Murray Gershenson, gets 5400, which was the second or third MBE machine that Burke and Elmer had made. And I'm the theorist, but I'm working with these gentlemen as experimenters. And that morphed into the fact that in '83, my senior colleague, Professor Murray Gershenson, decided that he didn't want to continue with the lab, and the deans and the chairs of the different departments asked me to take over the lab, and I said, you must be kidding. I'm a theorist. And they said, no, 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 you're the kind of theorist who could do this. So I got sucked into it. But the reason I got sucked into it is actually right here. I don't know how to point this thing as a pointer. Well, I turned it off. Did I turn it off? No. Well, I don't know how to point the pointer, to be honest with you. Is there a button here? This one? Ah, okay. So here is the thing. I kept thinking about the problem for about 6-7 years. And in the process, I read John Arthur's papers. I read Dr. Cho's papers on the surface reconstruction. That impressed me because I recognized, at least my prejudiced view was, that you cannot talk about what happens in growth unless you understand the detailed atomic structure of the substrate on which you're growing. So knowing the surface reconstruction, knowing how the surface reconstruction were indirectly, clearly connected to the stoichiometry, namely the amount of arsenic, etc., all what was very important. And as a result, all of these studies, and by this time, of course, so what we got started already is summarized up there. That my view back, starting from 73 and by 76, 77, absolutely firm in my mind. From that, it has never changed, rightly or wrongly. Has always been that first, this subject is dominated by thinking about not what films do on the substrate. It is absolutely the wrong way to look at the problem. It is how do films form on the substrate, because how they form controls what they do. So you have to understand that while all ground state thermodynamic theories and models and calculations, which are perfectly fine, nothing wrong with them, the real issue is that what applies to the sample you have studied? Growth, by definition, is the time-dependent changing number of particles evolving under each other's influence. That is a dynamic system. You have to understand the dynamics, which is governed by the kinetics. So as a result, the notion of equilibrium itself has to be understood. This is what I did in my first paper in 1983, which also introduced the entire idea of a kinetic Monte Carlo, except that I didn't use the word kinetic at the time. I just used Monte Carlo because to me, Monte Carlo is Monte Carlo. I didn't realize that there was a prejudice of 40 years of literature of Monte Carlo as a metropolis type of approach, which is at thermodynamic equilibrium. So in the initial days, had a lot of fights with the referees. Finally, somebody later invented the term kinetic in front of it, and all of a sudden life became easier for everybody. In any case, so that is what that is. So in the early days, with the postdocs, Jaspreet Singh and I, we did that. Now, the next thing I want to point out is this. So in 1982, Frank Gunther and I, along with some colleagues who are here, like Klaus Plug, and Art Gossard is not here, Pierre Petrov is not here, but let's see, Dr. Cho, I believe, was part of it. Anyhow, we organized this conference called MMSS. MMSS stood for Metastable and Modulated Semiconductor Structures. Leo Isaki was at this. I asked Leo Isaki and Paul Dewey as the two keynote speakers because I thought that the issue to me that is central to this whole subject, metastability, is what is represented here and indirectly here in these modulated structures. Well, Leo liked this conference so much that he asked that he wanted to take it to Japan as a rotation, now US, Japan, Europe, and so on. And I, at the time, insisted that we should hold it at every 4 years. That gives us time to have something to say at a conference. And the compromise was made, no, let's do it 2 years. So it ended up being in '85 fall in Kyoto. And Leo picked Sakaki to be the chair of this conference. And somehow, to my utter surprise to this day, when Frank Guntainer and I went to Japan to hand over and help organize the second one, we were told by Sakaki and the other colleagues that they wanted to drop the word metastable because somehow the word metastable was not very well understood, misunderstood, etc. And somehow the word metastable got dropped, and since then this conference is known as MSS, Modulated Semiconductor Structures, and I may say so publicly today, after '87, I have refused to attend that conference, except when it was the 20th year, and Gunther Bauer asked me and Frank to come as founding fathers of the conference. So then I went for exactly 10 minutes, spoke, and left, because I felt that my baby, my intellectual baby in this conference, is tied to the word metastable. Now, with that, I will quickly go through some of the specifics. But let me just point out something. The other thing that Dr. Cho has influenced me, so I can tell you very frankly and clearly in front of all of you. As far as I'm concerned, the teachers for me in this business are John Arthur, Al Cho, and certain things that have come from Bruce Joyce and Tom Foxon and Klaus Plug. And then, of course, my own friend, Frank. In 1985, Al had invited me to come and give a talk at Bell Labs. I remember that day for a very interesting and strange reason. When I arrived there, it turned out that Feynman was giving his talk on quantum computing on the same day, 3 o'clock. So when I arrived in the morning, Federico Capasso, who was going to be my host, said, "Hey, Anupam, at 3 o'clock, there'll be nobody here." I said, "Don't worry, I'll be the same place where everybody else is," which is Dick Feynman's talk. At that place, Dr. Cho, I'm sure, wouldn't remember because we were young, just getting started. He was already an admired master in the business. We were talking, and I said to him that, you know, the trouble with all this is that we cannot do the right experiments and several of them so that you have a total picture to understand something. Isolated, you can keep inferring that this is an elephant, but you never really know whether it's an elephant. And therefore, I set upon, in '85, with a colleague of mine, Ping Chen, who was my colleague at USC, to design an 8 interconnected chamber, but it was not the number of chambers, it is the function they provide. So here, there are 6 because we went wall to wall, and 2 chambers have been sitting actually in the warehouse since 1992 to this day. But in these 6 chambers, you can see there is a 3-5 chamber, which is a gas source chamber, but I have never been able to use gases simply because the building safeties never allowed that. There is a custom designed metallization chamber, meaning E-beam evaporation, and here is a mishap story. Michel, good God, Ribert, man, whose last name all of a sudden I'm drawing a blank. He became the president of Ribert and then retired a couple of Picot, there you go. So Michel Picot at the time was chief of the service aspects of a US Ribert representation. So he comes to install this thing, which has 4 E-beam evaporators and a linear hearth and a copper block, and he misaligned the damn thing, and he turned it on, and next thing you know, he just blew copper all over my chamber. So since that day, Ribert owes me a chamber, okay, in writing, okay, but in any case, so coming back to the main theme, you can see here what is involved. There is a focused ion beam assisted etching chamber. There is a plasma enhanced CED chamber, so you can grow oxidized nitrides, etc., to act as in situ masks. There is oops, great God. Oh my God, where's that? There. There is an ECR plasma etching chamber, and there is a UHV STM AFM combined. In fact, the world's very first commercially available later combined UHV STM AFM was made by Park Scientific Instrument in their garage before they became a big company, because I went to them with over 200,000. I said, you're a small company, we want to do this, here's the money, let's do it together. So this is the kind of system on which we have done a lot of work over the last 30 years almost. And I have very little time, I've probably gone over the time anyhow. So let me start by showing 3 or 4 illustrative examples in which the spirit I want to share with you is the importance of the one thing that people by and large have the mindset, well, arsenic or anion doesn't matter till you have enough. And yes, from a certain point of view, till you have enough will not matter, namely having less will matter. But you have to optimize it. And that optimization is the following. Once again, historically, the entire conceptual picture of crystal growth, if you look at the textbooks, hundreds of them, you will notice, starting from Mr. Gibbs, who gave the idea of nucleation, induced growth, etc. There have been basically 2 competing kinetic processes that are explicitly discussed, even though in real life there is a third one. The 2 are migration, surface diffusion, what I like to call it, competing against evaporation, going back to the parent phase from where the atoms or molecules come. Now, in all real things that we do, there's always some kind of surface molecular reaction kinetics involved. There's hardly any models that you can find in any textbook as a teacher that you can go to the student and say, go read about it, right? So that was the basic thing. So I'm not going to go into that, but here is what I wrote down in that 783 paper. And then here, I'm proud of it because this is something that we did by first doing kinetic Monte Carlo to represent our prejudices of what was going to happen, and then went and did the Reed measurement, and that is what is shown here. So this is the simulation of what the Reed intensity would do if you changed pressure or arsenic pressure, anion pressure, or temperature, and correspondingly the measurement and the correspondence between the two, at least in a qualitative sense, to begin to understand the importance. Then we introduced the idea of growth interruption in 1983, though in my group generally things don't get published till at least 2 to 3 years later. That is a mindset that is hung over from my graduate days when I finished PhD in 71 and never published the first paper, that too under tremendous pressure till 3 years later. So growth interruption is something we introduced in fall of 1983, and by the time it published, it is a little later, but you can see, oops, the topmost PL there, that is for continuous growth single quantum well. And the others are for interruption of growth at the inverted interface, that means gas on al gas, and on the normal interface, which means al gas on gas. And you can see how that line, which looked narrow and homogeneous, splits. And that splitting is a good thing. It says that now I have created local regions of width that can be well defined enough and in relationship to the exciton size. So the length scale that matters, it depends upon the kind of experiment you're doing and therefore the kind of physics information you're extracting. If you're doing a transport measurement, the kind of interface that you'll sense is exactly different or very different from if you're doing optical measurements. So on the scale of the exciton diameter, if the terraces are large, it sees a locally well-defined width, and therefore these variations correspond to exactly plus minus 1 monolayer fluctuation. Then you can create superlattices with interruption, without interruption, etc., etc. In fact, around that time in the 80s, in 1985, there was a PSR meeting in actually Arizona. And Herb Kromer and I got into a public debate, argument, if you will, about my statement, which was, I see no reason why an inverted interface cannot be as good as a normal. It is just a matter of optimizing, understanding and optimizing growth kinetics. So he and I bet a beer, and 3 years later, he had to buy me a beer. And that is inverted HEMS with liquid nitrogen mobilities of 170,000 and up, okay? All because of optimizing things. Now, another matter that was brought up by Dr. Horikoshi. He showed you measurements, reed measurement, which look like this kind of double structure. This is, in fact, from Frank Granthina's work in 1983-84, so a few years ahead of others. And when we saw this thing, this has to do with arsenic pressure and optimization. It occurs when you go to metal stabilized. And from the modeling in kinetic Monte Carlo and the kind of intuitive understanding of reactions at surfaces, because I also have done a lot of work in catalysis area, so I understand the significance of steps. And all reactions at steps generally are much faster than they are on planar place. So we could show from the kinetic Monte Carlo simulation that the competing reaction kinetics of arsenic, unless you build in the fact that at the surfaces the arsenic will react faster than at the terraces, you cannot reproduce this behavior. So once again, these are things that have been in the literature already for 25 to 30 years. Finally, again, the work of my officially Professor Gershensen's student left over from 83 that I inherited, Ming-Yuan Yen, who after finishing PhD graduated, and Dr. Cho kindly took him as a postdoc. That is that Yen over there. This material system now is indium arsenide, gallium arsenide, so there is 7% lattice mismatch strain, but that's not the important reason for showing this. The reason I show you this paper, which was presented at the International MBE meeting, in fact, in 1994 in Kyoto, I believe, and the MMSS meeting in Kyoto, sorry, in 85. In here, in this paragraph, there are 6, 1, 2, 3, 4, 5, 6 different ways that we have used MBE to grow. That includes all the things, including what we call alternate gallium and arsenic or cation anion deposition, which is also known as migration-enhanced epitaxy. That is right here. And the results correspond to these different situations. Okay? So the idea that the kinetics you have to control. Now, in migration-enhanced epitaxy, I give Dr. Horikoshi credit for coming up with that acronym, but the intellectual content of what the technique is already in this work, and it basically says that if you control the arsenic pressure, turning off the arsenic flux just says you have made the chamber pressure, background pressure drop fast. So it's a matter of the range, and most importantly, self-limiting incorporation, which anions have. Anions don't incorporate on anions under these conditions. So that is the essence. Finally, I shift to one other thing that came up in the discussion earlier today, and that is this idea that if Mr. Gibbs told us that if you have any surface that has curvature, then by definition, the surface curvature leads to variation of the surface stress as a function of position. In other language, we call that the capillary force. So we can pattern the substrate. So this is the work of my student Suprate Guha from the mid-1980s, in which we patterned the substrate in square-like or stripe-like mesas. And just the fact that you have now the gradient, by choosing the orientation appropriately, we can make the incoming gallium atom. So this is homoepitaxy, gallium arsenide on gallium arsenide, no lattice mismatch. Yet there is a strain gradient, stress gradient from the side wall to the top, or of course I can choose it the other way around. But when I choose it like this, I can reduce the size as I grow, and I can grow purely growth control in situ wires and quantum dots. And this itself is work from the late 80s and early 90s. In fact, in 1993, I already wrote a kind of review article on this subject. This is today the most prominently sought platform for single photon sources, which have sufficient uniformity and are in a regular array, so you can have input-output. We ourselves, my latest PhD students, are working on that 20 years later, although I had hired a colleague by the name of Dan Rich, who left in 2000, went to Israel, who had done Cathode-Lumsel studies on these things. So all of this is done in the literature. This is the kind of array that you get pyramidal. And at the top, if you do cross-sectional TEM at the top, that is where you have the quantum dot structures, quantum wire structures as you wish. So let me stop with that. I can go on with all kinds of other illustrations, but I thank you for your time. But most importantly, I thank all of you in the field who have inspired me, forced me to think harder, and all my students who have kept me on my toes, but hopefully I have kept them on their toes as well. So once again, thank you very much.
Thank you, Anupam. Another one of the MBE pioneers that dates back into the 60s and 70s is Mort Panish. We heard this morning from John Arthur and Al Cho about the early days of MBE at Bell Labs, and we're very happy that Mort's going to give us a few words about that era. Mort?
Can you hear me? Well, now for a total change of pace. I came here not knowing I was going to give you a talk. So what you're going to hear is the stream of thought coming out of an 85-year-old brain. And maybe it's a total fairy tale. I don't know. But I will tell you, because I guess I have to explain how I had the nerve at one point in my life to be Al Cho's boss. And so I'll give you a start. I got a PhD from Michigan State University in physical chemistry in 1950, and my PhD thesis was on the chemical thermodynamic properties of interhalogen compounds, things like chlorine trifluoride, iodine pentafluoride, very, very unfriendly chemicals. And about time I finished my research, my lab blew up. And well, sounds funny, but one person was seriously injured. And I decided I was going to work with more tame things for the rest of my career. And I went off to Oak Ridge National Laboratory and got involved with a rather insane project. At Oak Ridge National Laboratory, they had a project to develop a nuclear reactor to propel a bomber. And the reactor was fueled by molten salts. It was about this big, could power a city of 100,000 people. Ran at 800 degrees centigrade. And we actually did get the reactor going. It was a gorgeous, beautiful reactor. The idea of what it was for was insane. But I got the chance to do a lot of chemical thermodynamic studies of molten salts. And so that got me into the area of dealing with non-water chemistry, I guess I never handled a test tube as a chemist. At any rate, I went from there to Avco Corporation, where Avco had a contract to design the re-entry vehicle for hydrogen bombs.
and they had 5% of the money could be used for basic research. And I was one of the people who was lucky enough to get the 5% money. And there I got the opportunity to study the thermodynamic properties of very highly refractory materials. That included studying vapor pressures with Newton effusion cells. And actually I studied the vapor pressure of things like iridium and rhodium and osmium. And so I was familiar now with handling things at very high temperatures. And at one point, the Navy or Air Force, maybe who sponsored, I don't remember who sponsored this research, but they decided no more 5% for basic research. And so I would have to work on the materials for an actual reentry vehicle for a hydrogen bomb. And I was not interested in doing that, and so I left and began looking for a job. Oh, I should mention that when I first got out of graduate school, I interviewed at Bell Laboratories in 1954, and they didn't hire me. And they were absolutely correct in not hiring me. Later on, when I was in a position of hiring people at Bell Laboratories, I understood very clearly why they did not hire me in the first place. But after 10 years of experience, I applied for a job at Bell Labs, hoping that they did not remember my first interview. It was very interesting to be interviewed for that job. And at one point, I was speaking to Carl Thurmond, who was heading up a department there. And it was clear they wanted a chemical thermodynamicist. They wanted somebody with my background. And but he had a sort of twinkle in his eye, and he said, Mort, he said, you know, the physicists around here are trying to dope gallium arsenide, and they're taking a quartz capsule and they're putting a gallium arsenide wafer in, and they're putting a little zinc in. And he said, it failed. And what do you think happened? And I said, well, I think they got a puddle. And he smiled, and I knew I had the job at that point. And so I came into Bell Labs to do chemical thermodynamics, to do phase diagrams. It was obvious the physicists had no idea about what happened when you put these various materials together. They were thinking of silicon and the things you could do with silicon, which absolutely did not work with 3,5 compounds. And so I was doing phase diagrams of dopant materials with 3,5 compounds, of 3,5 compounds with each other. And I was like a pig in mud. I was so happy because these phase diagrams came out looking like the phase diagrams I studied in undergraduate school in physical chemistry. They were the idealized phase diagrams. They were so beautiful looking. But at one point, I realized that I was doing this work, but all around me was an intellectual fervor going on that I didn't understand, because I had never studied anything about solid-state physics. And so I went to Carl Thurmond and John Galt, who was the next level up management, and I said, I'm really having a lot of fun doing all of these phase diagrams. It's something I like to do. However, I'm uncomfortable because I didn't understand what was going on around me with all the physicists. And it's something I don't think that can happen nowadays anywhere, but they sort of huddled together, and then they came out and they said, well, take 6 months. Take 6 months, just study for 6 months. Ask anybody in Bell Laboratories any question you want to ask them. And so I spent 6 months learning solid-state physics. And at the end of that time, which is now getting to be around 1966, I was feeling fairly comfortable that I understood simple solid-state devices and stuff like that. And in early 1967, John Galt, who was one of the most brilliant managers I have ever come across. John Galt called me into his office, and he called Izuo Hayashi into the office. I had never met Izuo. And John drew a picture of a semiconductor laser, of an injection laser, just a plain diffused junction in gallium arsenide. And he explained to me, to both of us, the problems with all of this. They had very high thresholds. They could only be run of a very short duty cycle, et cetera, et cetera. And he said, someday somebody is going to get a CW laser, one that will work continuously at room temperature. And he said, I want a few people working on this, but of course at Bell Labs he couldn't order us to do it, but he could sort of pique our curiosity about it. And so he did a selling job on Izuo and me. We knew very little about lasers, and he just sold the project and finally said, will you do it? And I looked at Izuo and he looked at me, and yeah, we'll give it a shot. And so they moved Izuo into a laboratory next to mine, and that collaboration started. And I was studying at the same time as I was doing the phase diagrams. Before this, I had been growing some crystals for Hans Kleiser, and Hans was studying the luminescence of these crystals, and we knew that crystals grown out of the liquid, out of liquid gallium, had a better luminescence than any other galliumide crystals you could find. And so with that little background, Hayashi and I began looking at layers grown on gallium arsenide from liquid gallium. And we had a lot of false starts, but at one point we attended a talk and we heard Hans Rupert from IBM describe a lattice-matched layer of aluminum gallium arsenide and gallium arsenide. And Izuo looked at me and I looked at him, and we knew this was the answer to our problem. We went back, actually we ran out into the hallway of wherever this, I think it was in Las Vegas, I don't remember exactly. We ran out into the hallway and we were drawing structures that we could grow with this lattice match stuff. And the first thing I did was grow a single layer of aluminum with a very simple apparatus, a single layer of aluminum, gallium arsenide and gallium arsenide. I had already studied the phase diagram of that system. And And he looked at the luminescence of the gallium arsenide under the aluminum gallium arsenide layer, and it was really bright, brighter than anything we had ever seen. And so we were off and running. And we worked for several years on this, and eventually we did get a CWW double heterostructure laser. And I realized at this stage that I had a tiger by the tail. This heterostructure business was obviously going to explode if the structures could be grown, because you could dream of an incredible number of things that you could do with heterostructures if you could only grow decent layers. And I also understood very clearly that although we did manage to make this CW laser with liquid phase epitaxy, that liquid epitaxy was not the technique that was going to do this, because it simply didn't have the capability of growing such very thin layers under extreme control. At some point around this time, I was promoted to be the department head. I was talked into it, actually, by Sid Millman. You remember Sid Millman? And I remember I was skeptical about taking a department head position. And I remember he spoke with a Yiddish accent. He said, "So you'll travel?" And I said, "Oh, that's nice, I'll travel, okay." Eventually, they did convince me, and I took the job. And I had a group of people working in this department that were really, really outstanding scientists. And in my opinion, every one of them knew much more about what he was doing than I would ever know. And so my job was not to tell these people what to do. My job, I had two major jobs. One was this horrible thing they called the merit review at Bell. Remember that, John? The merit review at Bell Laboratories, where the department heads had to defend their people against the other department heads, because that pot of money was going to be distributed as raises. And the other job was managing the money in the department and getting the money. That's where the problem with Al Cho came up, because I realized that Al had a technique that could explode this heterostructure business. That was the technique that I believed might succeed. But to me, the first proof that it was going to be practical, that it was going to be able to achieve anything, was that he had to be able to make that laser with MBE. And I had to fight backstage. I had to fight to get the money to provide the equipment for Al. That was my major job for Al Cho, was get money for him, which I did over the objection of some of the other department heads who fought me, and who predicted that MBE was going nowhere. And so I sort of staked my reputation on supporting Al Cho, and I sort of prayed that he was going to be successful, and he was. And so all of this grew out of just that, the way those things happened at Bell Laboratories. A wonderful management, wonderful people around us, the ability to speak to people who knew so much more than we did. each of us could find people who knew so much more than we did about it, a given thing. So that's basically my story. I have just another few comments to make. You know that philosophers have been studying the field of epistemology since the time of Plato, and that's the question of how do we know what we know? Do we know what we know? Do we know what's the truth? And the sobering thing you have to think about when you think about that is that in the year 1900, every theory in chemistry and physics that we had that was producing wonderful things, the economy was changing because of science, because they thought they knew what they knew. And in the year 2000, every single theory in chemistry and physics that had existed in the year 1900 was totally overthrown. So we all talk about here about our theories and everything, but in the year 2100, they may be saying they didn't know what they were talking about. And that's all I have to say. Thank you.
Let's thank our speaker again. Our next speaker is going to be Ralph Dawson, where I think he's going to talk about some of his experiences about MBE. Sure.
Okay, thank you very much. In fact, when you're talking about it, we were asking, did you get your PhD when you were 20 years old? Not very far, 21, the man says. Okay.
This goes.
I want to take this opportunity to have 1 minute by telling you a story, okay? I have written something on record. I pointed out Darwin's theory of evolution applying to living things and all that, okay, should apply to technology. Because if your technology is not good, you go bankrupt.